Hi everyone, my name is Joe, and on today's video we're going to be covering the topic of linearization and how do you use it to approximate the value of a function at a given point. Okay, so very often for problems like this they're going to give you a function and a value from which you have to approximate and the value for which you have to use the linearization to approximate that number. Okay, so let's say, for example, that they ask me to approximate the value of the tangent of pi over 3. So in this case, in this scenario, my function is going to be the tangent of x. And they ask us to use the linearization at the value of pi over 4. Okay? So what does it mean to linearize the function and to use that to approximate the function? Why is that a reasonable assumption to do? Basically, the linearization is very similar to what we did in the previous video, so check it out if you don't know exactly how to find tangent lines. Because the whole idea behind linearization is that if you have the graph of your function, when you find the tangent line at a given point, if you zoom in your function, so let's say I'm zooming in here, what I would see would be something like this. And you see that very near the point of tangency, the tangent line is very close to the function, okay? So that's why when you're calculating the value of a function, you don't really have a very good way to calculate. You can linearize the function near the point that you're trying to calculate, because if you see, when I go farther from the tangent line, I can get any type of error. So this is only really a good approximation as long as I'm doing the linearization to a point near the point that I'm trying to approximate for my function. And it really depends. Something that you'll later learn on, which is like the Taylor expansion polynomial that works for analytical functions, is that you can work with higher degrees of polynomials using higher degree derivatives, and that tends to give you each time a better and better approximation for your function, and that's very often what computers use sometimes when they want to approximate, but you have more like small ways to approximate functions nowadays, and that's not even something that I do very often on the day-to-day, but just let you know. But anyway, all right, so the first key aspect of this whole idea is that, for example, the value of my function is very close to the value of the function itself. So generally we have the line equation like this, right? So now I'm just going to use a little notation. So I'm going to use a big L with A, calculate at x, just to use a L to clarify that that is the linearization. In here is going to be very straightforward, the point in which I'm calculating the linearization. And by putting the x here, it's clear that that is a function notation. So it makes it clear what I'm about to say. So basically what's going to happen is that the linearization calculated at a point is an approximation of my function at that same point, as long as the a is closer to x, okay? So basically this means that the value that my function obtains here is very close to the value that the line obtains for the same value of x, all right? So first I need to find the linearization, which is nothing more than a fancy way to call the tangent line at the point pi over 4, f of pi over 4. And with that tangent line, I can just approximate the value right away, okay? So basically what I'm saying here is that the tangent of pi over 3, which is the number that I'm asked to approximate, is approximated by the linearization at pi over 4, calculated at pi over 3, okay? So if I found the linearization at pi over 4, which is the tangent line, all I need to do is replace the x by pi over 3 in that function, okay? All right, so this means that if you remember from our previous video, one of the first steps is that I need to find a point throughout which the tangent line is going to pass through, which is pi over 4, f of pi over 4, but the tangent of pi over 4 is 1. Okay, so this is exactly the point that I have to pass through. And I also need to have the derivation of my function. And the derivation of this function, you can write tangent as sine over cosine and use the quotient rule. And you're going to have to use the trigonometric identity, sine to the power 2 plus cosine to the power 2 is equal to 1, to get 1 over cosine to the power 2, or x, which is also the sec to the power 2 of x. But I need to have the derivation exactly at pi over 4. So the derivation at pi over 4 is going to be 1 over the cosine to the power 2 of pi over 4. The cosine of pi over 4 is square root of 2 over 2. So this is 1 over square root of 2 over 2 to the power 2. Every time you take a number and divide by a fraction, you flip the fraction multiplying. And the power to a fraction is distributed. So power 2 to the root is 2. Power cancels the root, so it's 2. And the power 2 to the 2 gives me a 4. So it's in reality 1 over 2 over 4. And I flip multiplying. So it's 1 times 4 over 2. So it's exactly 2, right? And it passes exactly throughout this point, okay? So this means that my tangent line is y is equal to mx, where m is my angular coefficient, so 2 times x plus b, same as we did in the previous problem, on the previous video, sorry. And I just replace the point throughout which this tangent line needs to pass through to find exactly the value for the constant b. So y is equal to 1, and x is equal to pi over 4 plus b. So this means that my constant b is going to be 1 minus 2 times pi over 4. Okay, this is exactly the value of b. So this means that my linearization at pi over 4 of x is exactly the equation for the tangent line at that point. So it's going to be 2x plus my b, which is given here. I'm going to put in parentheses. I could simplify the 2 with the 4. I'm just not doing that exactly at this second, and I'm going to see why soon. Okay, so this is exactly what I'm asked to calculate and to simplify. So let's look back at the original problem. So to approximate the tangent at pi over 3, I need to calculate the linearization at the point pi over 4, calculated at pi over 3. So this means that I want to put the pi over 3 exactly inside of the value of my function x here and find out exactly what I get. So this is going to be 2 times pi over 3 plus 1 minus 2 pi over 4. I can put in the in Avness the 2 here. Okay, I'm just going to erase here the bars. So as I was saying, you can put the 2 in evidence here to get pi over 3 minus pi over 4 plus a 1 here. And pi over 3 minus pi over 4, if you do a cross multiplication, you're going to get is exactly pi over 12 plus 1. And I can simplify here to get pi over 6 plus 1. Okay? So this gives us pi over 6 plus 1, which is a good approximation for the tangent of pi over 3. And this shows you how strong the concepts of derivations are, and most importantly, it really depends and boils down to where does the definition come from, right? Like very often students, they just memorize the definition. It gets hard to apply to a bunch of different other scenarios. But the key aspects to all applications of the derivation is what do they represent? They represent the angular coefficient of the tangent line. So if you want to approximate the function, you can calculate the tangent line by using the derivation and the point. If you want to find the max and the mins of a function, you can see that they are represented by hills or valleys. So they're represented and given by derivation equal to 0 or not being derivable. Anyway, like all the application of derivatives come in much easier if you always have in mind where does the definition come from, okay? So I hope this clarified the topic to you guys. I hope it helps. If you have any other questions that you would like me to cover in the future, please let me know in the comments below. I'll be sure to check them out and reply, and also post videos on those topics in the future. Have a nice day. Bye-bye.